Yaskawa.
You're watching the PLCopen Basics video tutorial series. This video shows PLCopen homing and 0-point set. Hi, I'm Matt Pelletier. Let's proceed in the class project to build an automatic homing routine for each axis. We'll use home pulse for one axis. That's a block from the PLCopen toolbox. And on the other axis, we'll do a simple 0-point set. Homing may be a familiar topic for those of you seasoned in the motion industry, but I would like to go through and just introduce and define what homing is. As it says here, it's a repeatable move sequence to move the axis from an unknown position to a known position. So when the machine powers up, that encoder hasn't given any pulses yet, and so it doesn't know where that part is. That's the case of the incremental encoder. You can't really talk about homing unless you also talk about absolute encoders. And the reason for the absolute encoder is to completely bypass the need for homing every time you power up. You would have to, at one point, set the absolute zero position when you commission that axis, but it would very infrequently need to be homed when you have the absolute encoder. You may recall that on this demo, we've set both of the motors to be incremental, so a homing routine is appropriate. You may know that when you turn on a machine, it's typical to see some sort of slow calibrating move when you first turn it on, and that most likely is the homing routine. And it's going to be moving the load until it hits some type of sensor, a prox sensor, an overtravel sensor. Maybe it's just looking for the reference pulse once per revolution on the encoder. Could look for the hard stop, making use of torque limits of the motor. There's all sorts of ways to accomplish homing. And so that's where PLCopen comes in, with PLCopen Part 5 to define homing. We should refer here to the source, plcopen.org, and you can see that it's Part 5 homing. So PLCopen has these two definitions, homing procedures and homing steps. The older original method was to use these procedures, and now the new method that gives you more control over your homing sequence is the homing steps. And the thought with these homing steps is that there's not just one block or even a set of blocks that would satisfy all homing requirements for all machines. PLCopen is just defining what are the basic building blocks or the steps of homing. And those are called MC step in the PLCopen Edit Wizard. And that's why if you look here in the Edit Wizard of your software, under PLCopen Plus, you can see the MC step limit switch and MC step ref pulse, also MC set position. And these are the supported function blocks by Yaskawa's MPIEC controllers: MC step ref pulse, MC step limit switch, MC finish homing, and MC set position. So I'd like to just quickly describe each of these. MC step ref pulse uses the reference pulse of the encoder. Every encoder should have a once per rotation reference pulse. Just click my animation here. So the motor moves until it finds that reference pulse, and then will even move backwards to line up with that reference pulse. I'll just show that again here. Moves, finds reference pulse, moves back to line it up. So that's what MC step reference pulse does, and you give it the direction, the velocity, the final position, and then any limits that you'd like to be implemented while that motion occurs. MC step limit switch applies to homing specifically to the overtravel inputs that with Yaskawa are wired to the servo itself. In my little animation, MC step limit switch would look something like this, where it moves toward the negative overtravel and then abruptly stops at the limit switch. So you can see this block has the same type of inputs with a configuration for the switch itself. Let me just make this clear of which inputs can be used with MC step limit switch. It's only the overtravel inputs wired to the servo pack. So in this demo, really the only way we would have is to turn on these two, SI1 and SI2. Those are the overtravel inputs on the demo case. At this time, we don't have input manipulation implemented in this training, so we will not be using that method of homing. But MC step limit switch does not mean homing to any input anywhere on the system. It means specifically homing to the over-travel designated inputs. There's a block called MC Finish Homing, which I'll discuss next. And of course, MC Set Position, where you just arbitrarily set the position to any value. And while we did use that in a previous section of this training series, we'll do a little bit more formal and complete implementation of MC Set Position coming up here in a couple minutes. One thing to remember about homing is that homing is a PLCopen state that the axis can have. So if you use the MC read status, tells you the state of the axis, and this could tell you whether you're in the homing state or not. And depending which blocks you've used to go into that state, they may leave it in the homing state. And so to finish and leave the homing state, you may need to use the MC Finish Homing block. This is specifically to be used with the MC Step Limit Switch. After you hit the limit switch, you will still be in the homing state. So if that's the last thing you wanted to do with homing, you would execute MC Finish Homing. Very well, let's now add homing functionality to our project by creating the home program POU. I think you'll be able to follow along with me on this one. So go to logical POUs like we've done many times here and create a program, call it home and ladder. We'll go down to the medium task this time and insert the program instance for home. Home and home. And here I'll introduce the homing style that we'll use for the rotary axis. It can be on the right-hand side here of the demo. Do that one first, the rotary axis. And for this one, I'd like us to use the PLCopen toolbox, which uses a block called Home Pulse. And the secret to using this correctly is to use the home structure, which is part of the axis struct structure, and then to set the appropriate parameters for that. And I've pulled those out here. The most important ones you'll need for home pulse are the ACDEC, creep velocity, offset, and offset velocity. Now you're not going to know what the offset is until you home it with a 0 offset, and then go back and try to determine what the offset should be. And we're adding a little logic here to let us know when that homing is done so that we can set a status, which is also a part of the home struct. The .homed element tells you whether you've homed or not. And then if for an arbitrary reason you need to reset that home status, you can do so. Or we're using a system variable called PLC mode run. And this means whenever the PLC is not running, it will reset that homed status. Otherwise, this will lock in the homed bit with this seal-in circuit. You can use this status then to prohibit motion elsewhere in your program until the axis has been properly homed. And just real quick before we get started, if you look inside the home pulse, double-click to open it, the core of home pulse is simply an MC step ref pulse, moving to the reference pulse, followed by a move relative for that offset distance that you'll put in there. And this is also a good example of how you can create your own function block that involves motion when a sequence of moves are required, by using this technique here to take the outputs as a seal in to keep the execute running. Okay, so go ahead and see if you can make this work, and then I will, as usual, show my solution. Okay, here's a solution for homing the rotary. We'll do a home underscore pulse and add the rotary.ref. And now we'll execute with the existing g underscore home. And for the home data, we'll use rotary.home. Now, if you're using the MP2600, you might rather home the real axis, since this rotary ends up being virtual on the MP2600. So you can use screw.ref and screw.home here. Now we'll add the rtrig, enter, enter. Broke that up, oops. All right, fix that up. Now make it look nice here with the ladder. And we're making a new variable here, local, called home done pulse, and we'll make that a var, a local var. And now down below we'll seal this in here with a new ladder network using that home done pulse to turn on the rotary.home.homed. Now, if this bothers you that it's not showing the entire name, you can go to Extras, Options, Graphical Editor, and there's this option, 2 lines for name, and you see that'll let it wrap here. Now we're going to use this to seal in. One way to do this is just copy it. Save a little time to just paste that in here. If I click on this line, I can do another contact. I'll make this one normally closed. This one was called 0 set clear, local var. And now if I do parallel, all right, you notice that it kind of connected all these nodes together, and while that really doesn't change the functionality, if you don't like that, I'll just do here undo and move it over a little bit and then add it again. And this one is going to be the system PLC mode. There's all these different PLC modes that can be used to your advantage. I wanted PLC mode run. And when the controller turns on and goes to run state, we need that normally closed, we'll find that the homed status will be automatically cleared. So now we do need to give some values to this rotary.home variable. We can go to the view initialize multi-element variable window and go back to the globals here and take that rotary axis struct and come on down here to the home section. We needed acdec to have an initial value over here. Be sure you type in the initial value column. I wanted 3600.0. Wanted a creep velocity of 45.0 degrees per second. The offset we don't know yet, but the offset velocity could be set to 360.0. Of course, you can experiment with these. So now let's download changes. Now I'll start the controller. And my servos are enabled. Looks like I'm already pretty close to home position. And so I'll turn on here the home input. You can see it's moving. And in the home POU, you can see that it's completed and the home done is turned on. However, it's not really in the right spot. So you can look at this rotary.homed in the watch window. I'm scrolling down here to confirm. I don't have any offset. So you can look at this and maybe you could try to estimate what do I think the offset is to get back to 0. And it looks to me like it's a clockwise about 90 degrees, maybe a little bit less. So let's try. Now if it's clockwise, that would be negative 90.0 degrees. And in HMI we can hit home again. So it's moving, looking for that C pulse. The reference pulse is right about here. Should turn around and go, yeah, it went 90 degrees. If you're happy with that, this will be different for each demo. If you happen to have the exact same demo, then you'll have negative 90 also. But otherwise, just go through that, run it with an offset of 0. That'll show you where the reference pulse is, somewhere within one rotation. And then just estimate the number of degrees. And by trial and error, you should be able to calibrate that home position. Once you've determined what this offset should be for your particular demo, you really should take the time to go back and initialize that, leaving debug mode and going back to this global variable, rotary, and come down like we did before to the home element. And for the offset, type in that initial value. In my case, negative 90.0. And also on this, I had mentioned that you could double click to open that up and look inside. And here we can see the MC step ref pulse at work, MC move relative at work, and it finishes it off with a set position and setting the error outputs here at the end. So that's home pulse from the PLCopen toolbox. Now for the screw, I think you remember that back in the beginning when we did positioning, we did have an MC set position already for the screw, and we just put that directly in here. But let's make this formal here under the home POU. And right below the rotary homing, we can put in this set position for the screw. So this set position will just be an arbitrary one-time set position, and if you have an incremental encoder, it'll be lost, and you'd have to manually calibrate that 0 point again. So this works really well when you have absolute encoders, just doing a simple set position. And the screw.home.homed will be retained on power cycle if you set the screw variable to be retained. So refer to this code and let's implement this here, and I'll show you my answer. Continuing with set position, we have this HMI parameter G0 set. There's a place for the position for screw.home.position. We'll have to initialize that one. Now for an rtrig, type rtrig number 2, connect that up, and make this ladder, calling this 0 set done underscore pulse. And similar to the above, we'll create a latch circuit with that same one, 0 set done pulse, to the screw.home.homed, which is the status bit. And put that one here to lock in, screw.home.homed. And we do need a way to clear that one. We're going to call it 0 set clear, normally closed. That's the same variable as used up here, so apparently this would clear both of them at once. That could always be changed to a separate variable. So the screw home position in global variables will go to the screw and look in your initialize multiple element variables down into the home, and there's the position. And you could just leave this alone if you want the home position to be 0. I'm going to type it in here anyway just to confirm that I do want 0 to be the position used by this block, MC set position. Alright, download changes. Now I'm in debug mode, and similar to what we did before, we can jog the screw till it gets roughly to 0. So I think it will be advantageous to change that jog speed in the manual POU here. We've got screw.jog speed, maybe 10 degrees per second. Tab, overwrite. Now we can control that a little bit more easily. Oop, wrong direction. Okay, so that looks like a good 0 point. So we come down here to 0 set. Yeah, so 0 set happened. And the screw is homed. Now we'll see what happens when we do a power cycle. So if we remove the 0 set and the home command, and in project control, we stop and warm start, you see that now we're not homed anymore. And in the case of the home pulse, that's no problem, because you'd want to have to home again every time you cycled power. But if this was an absolute encoder, now it's telling you that the absolute position is no good anymore. And one way around that, go to your global variables and be sure that that screw variable, that axis, is marked as retain. And that will retain every element of that entire variable. Of course, that is a programming change. So download changes. And now in debug mode, let's see what happens when we 0 set. And now stop and warm start. Because it's retained, the screw.home is retained, but the homed is not. So one more time, we'll home and 0 set. Okay, so rotary's homed, screw is homed. Now stop and warm start. And the screw is homed. If you do a cold start, I think you'll imagine that the screw will have to be homed again. But cold start only happens when the machine's running the first time that this project ever runs on the machine. So when you're first commissioning the system, that is what you'd want to have happen. And so this is one simple way to implement both homing and set position using these PLCopen blocks. So let's wrap this one up by doing a save to zip. And we'll call this one 11_homing. Choose zip project and zip. Thank you.